Hey everyone, it's Ryan from WM Guitars, and today we will be going through the Breedlove sound optimization process. So this is going to be quite a technical video. It's a reaction to how they optimize the sound on their instruments and the processes behind it. So we'll be doing a bit of a deep dive into their processes, but I'll also be telling you a bit about the history of how these processes have come about. So let's just dive right in.
Welcome to Winter NAMM 2021. We're excited to have you here with us. While disappointed we can't visit in person, we're glad to show you what Breedlove is all about. Guitars are our absolute pride and joy, the passion in our lives. Here's a look at the sound optimization process for our made-in-bend guitars. It's in our DNA across the line. Let's get started. Sound optimization. Why do Breedlove guitars sound so good? At Breedlove, art, inspiration, science, and craft merge in a process we call sound optimization. Sustainable, clear-cut, free, made-in-bend models are individually hand-voiced, with experienced luthiers meticulously tapping and analyzing variable, carefully milled exotic tone woods, sanding to weight and shaving away tiny, fragrant curls as they target specific, consistent frequencies that will make each unique instrument sound its very best. Tops, backs, and sound holes are specifically tuned to one another to create light, responsive guitars with superior tone, projection, and sustain. The same research and commitment is applied to the solid-topped, designed-and-bend instruments, which, while not hand-voiced, afford similar quality tone, finish, and construction at affordable prices. Sound optimization. You will sound better, and play more on a Breedlove. Greetings, everybody. We're behind the scenes here at Breedlove.
So that's just like a overarching kind of description on the whole process as a whole. This is the deep dive. It's a very interesting process that not many companies follow, so it's really nice to see that not only the custom shop made in bend models have this full process, but even the designed in bend models, which are made in China, they also have gone through the same scrutiny and will have some form of sound optimization within, although not quite as intense a process as they go through in the Bend factory.
In the workshop in beautiful Bend, Oregon, we are going to learn about the sound optimization process. This is a really cool technique that we use to make our guitars sound better than we ever thought possible. Good morning, everybody. How are we doing?
Morning. How are we?
Good. So this is the sound optimization room, am I right?
That is correct.
I'm in the right
spot. This is
spot?
where they all start, right in here.
Okay, that's a very, really very minimal bit of soundproofing.
Deep inside, behind the scenes of the custom shop in Bend, Oregon, and we're going to learn about sound optimization.
Correct.
Yeah. All right, what's going on?
So, as you can see on this shelf here, they all start in a somewhat raw form. These are all top sets on the shelf.
These are all guitar tops
These
right
are
here?
all guitar tops one day, just not, right
wow,
away.
There's a ton.
We got a lot of stuff here, but yeah.
And they appear to be sorted by maybe different species, by different sizes. What's going on with this sorting?
That is correct. It is mostly a species sort, but we also do mess with stuff like you said with body shapes, and so we know what's going to work for what.
Okay. So you're cataloging all this wood, you're sorting all this wood in here. And this is the wood that we're talking about. These are the tops and backs.
After Ian pulls the raw top, he'll go sand it to a uniform thickness. That's what you're looking at right here. This is an Adirondack spruce top that's all been sanded to 170 thousandths to get us started.
Okay, I don't know what that means, but it sounds pretty. It sounds pretty impressive.
That's 0.17 inches.
All right, so
I'm no good with imperial measurements.
Why are you sanding these guitar to a certain thickness? What's going on with that? What does that mean?
So we do it so that
probably about 3.5, 4 mil.
We want a uniform thickness so we can get a really good measurement of the top set's resonance, which we'll get into here in a little bit. And we're gonna how we figure out what's gonna make the most sense for sound optimization is we enter in all the data points. So in addition to getting a uniform thickness, he's also going to get the weight behind us here. I'm going to go ahead and flip this scale on. He's going to weigh a top set as well. He's going to
Love how the
measure
label
the
printer
length
has a
and
little
the
face
width
on
of
it.
that.
So it starts
And then there's a
spewing
couple
out
more
labels.
data points that we enter to try to figure out exactly what final thickness we want to sand all these tops to.
Okay, so every single piece of wood that comes into the workshop here, you guys start at the very beginning. You do some analysis. You take
Exactly.
you take these pieces of wood and you start to test them so you can understand the inherent qualities of this piece of wood.
Correct.
So you're studying the weight.
Yeah,
You're
yep.
studying the density.
Exactly.
You're the flex, all of these things, right?
Absolutely correct.
Okay.
Because I mean, you know, even though a lot of these wood sets are the same size, might even come from the same log, there's lots of variability in the wood. The grain's going to be different. It means the wood's going to behave differently. So we're going to try.
That's a very fair point. So a tree, trunk to tip, or root structure to tip, there can be up to 30 degrees variance in that one tree in things like density, weight, width of grain, which will affect the density, the amount of flex. So the closer you get to the root structure, generally the more dense the wood ends up being. So if you take a portion from the bottom of the tree, it's not going to react the same as a portion halfway up or towards the top of the tree. So these are all things to keep in mind. When you're building a guitar, a lot of factories just say, we need this wood at this thickness and put it on everything. They don't really take into account which portion of the tree that wood's come from. They just build to a certain thickness and off it goes.
And measure a lot of this stuff to figure out what makes the most sense to where we're going to sand this top to, and just try to make it sound as good as possible.
Well, I think that's the key word there. So you talked about variability, and let's talk about variability a little bit for folks at home. When we think about a tree that's growing in the forest, that tree can be very, very different from the bottom of the tree all the way to the top, and that density can change, and the different qualities of that tree can change up to, I've heard 30%.
I've heard the same thing, yeah.
So 30% variation in one tree.
Right.
And that's not even, identifying maybe tree to tree, just so much variability.
Not to mention species.
That's brilliant.
Species, I mean, obviously, they're different.
They took the words out of my mouth.
So we get different targets for how thick we're going to sand these tops to on every piece of wood. So no two guitars are the exact same, because no two pieces of wood are the exact same.
So we're gonna take every single wood set. It's gonna come in. You guys are gonna study it. You're gonna learn about the inherent qualities of that specific piece of wood, so you can identify how you need to treat that as you build this guitar.
Okay. So we've checked everything so far in terms of dimensions, but there's one last bit here that we're going to show you that we haven't checked. We're going to check the resonance of these top sets.
Okay.
So we use this microphone that he's got there by his mouse and this program here to measure resonance. What he's going to do is he's going to get it to record him. He's going to hold it just like that and give it a tap.
Tap that one more time for me, would you?
Okay.
You're going to tap it there. The microphone's going to read it, and then you're going to get a reading up here. Give me one more tap, just.
So what you're looking at here is basically like a frequency curve of what that ring of the tap of the wood is actually doing. So the top line above all of the others, that's the highest, that's the peaks across that whole fundamental frequency spectrum. And you have a couple of peaks which are much higher than the others. This is quite interesting, the way they're doing it, because I mean it's hard to see, but I can see down at the bottom along the x-axis, they're basically measuring the sub-frequencies, not the top end of the spectrum. So they want to see where those fundamental root notes are going to be within the resonances. So say an A is 440 hertz, that will just double all the way up the frequency spectrum. So if you've got a peak at 440, then the next peak will be 880, and those will share a similarity. So you only need to really measure a certain width of a frequency spectrum. Before it's just like copy and paste, basically. It obviously will react differently the further up you go. However, what they're looking for is just fundamental root notes here.
I can show folks at home what this looks like when you get a reading. Yeah. So you tap it.
Yeah, give it one more. It's harder than it looks. There are sometimes where you'll give it a good tap, and you gotta hold it in just the right spot so that the wood kind of vibrates in your hand.
Gotcha.
I think the talking's kind of throwing it off a little bit.
And you're looking at these different peaks.
You're
starting to read these graphs and understand the inherent qualities of it.
You can see now that the graph goes probably up to about 350 hertz. So that is all subspectrum, and you can see a peak just under 200 and probably around, what's that, 10, 20, 30, 40, just underneath 50 hertz as well. There's another large peak. So the 50 hertz will probably be the fundamental frequency, and your peak just under 200 hertz will be a resonant frequency. That's what I'm imagining from this. So the fundamental is kind of like your root, and then your resonant frequency is basically what that wood is ringing at. So if you were to put that have a frequency generator that can generate a single note frequency and put it on that bit of wood, then that whole bit of wood would ring a lot louder at that frequency than any other frequency, and that's due to the size. So a good comparison of this is like a room. So imagine a completely square room with walls that are completely reflective, non-absorbent. You will get what's called standing waves in that room, where the wavelength has, the sound waves have a certain length to them, and if they exactly match the length of the room, then it will bounce back completely on itself and double in frequency. And these are what within rooms is what we call standing waves. There's a lot of different names for them. Tangible waves bounce back just left and right, but then you get ones that bounce off the corners on 8 different axes. So there's lots of different categories of standing waves or resonant frequencies. And if you think of that plate of wood as being a room, it's long, it's thin, but it's rectangular. That frequency is traveling throughout that piece of wood exactly to the length of that frequency sound wave. So when that wave hits the other end of the wood and travels back on itself, it's actually doubling in frequency because that's the exact length. So when they start gluing this bit of wood together, chopping bits off the top and the end to like size it up to make a body, that will actually change, and you'll start to see some of that movement there.
What it's doing there is it's measuring the resonance of the length of this piece of wood and the height. We enter all that stuff in, including all those dimensions we talked about.
Yeah.
And we get an idea of where we think this top should land when it's done.
So every single piece of wood that's coming in
That's
here,
a very
you
basic
do this
way of putting
analysis,
it, but
you understand
if you imagine
the
that piece of wood like a
and
room,
then you record all that data,
and we print it out
you're
on these little
measuring
labels so that the
sound
guys can
waves,
see
the
going
lengths of the
forward
waves.
exactly where we need to sand it to. So these 3 things we have on the left here are actually kind of designating which body shape it's going to be.
Gotcha.
So we decided this one is going to be a more heavy player or a strumming guitar. So that for this body shape, for this exact piece of wood, that's how thick we're going to sand the top to. That's 96 thousandths of an inch.
Wow. So when you do this analysis, you understand all these different properties, but you also can start to understand what this piece of wood really wants to be, even from a playing style.
Right, exactly.
That
We're
is
thinking about it
mind-blowing.
more than just, we don't
is
do
so
anything
cool.
to spec, so it'll change. That number would have changed if we were trying to make it into a more versatile instrument like our concert body shape,
So
Or
they've
finger
obviously
stems,
got
like our
some
concertina.
spreadsheets.
Okay, and then you start to take this guitar and you
With,
start to build it. And
kind
folks,
of
if you're if
some
you'd like to see
automatic
the build
sums which are
process, we go
happening,
through
which
that
tell
in
them
a lot of
exactly what
detail,
thickness
actually,
they need
in
to
another
make
video,
that
which is a live tour
to get
of
that
the Breedlove workshop.
resonant or fundamental
You arrive at a
frequency
point where the
hitting just
guitar
right.
has been, the top has been put together, it's been braced, it has this bracing.
Right.
Talk to me about this part of the process. What happens next?
So, like you said, the guitar's been braced, but when you add all those braces and the bridge plate and all this other stuff, you're going to add a lot of changes to that flex in the wood, right?
Gotcha.
What we do is we put that top and the back, we do it to the back as well, in this mold over here.
Okay.
The mold simulates how the top's going to behave when it's glued onto its sides. And we're going to measure it again to make sure everything seems like it's right on target, and we're probably going to make
Super
a couple
beautiful.
little changes.
I love that tool.
Okay, let's check it out.
So again, it's going to be a tone tap here with the microphone and the little rubber mallet thing.
Okay, so we're going to take this microphone, we're going to tap this guitar.
Right on the bridge plate. Ooh. And he'll get another big old peak that you can see there. Yep.
Wow.
So you can see how far that fundamental's gone down. I know it's a different bit of wood, but now that they've shaped it, they've added the mass. The peak was just below the 200 hertz line, and now it's right in between the 100 and 200 hertz. So you're looking at like 150 hertz here. So it's the resonant frequency is actually dropping quite considerably once
You feel
they add
that,
mass.
folks. You probably couldn't hear that as well as on these small microphones, but you can feel that tap in your chest. It's like this resonance that bounces in your chest when he hits it.
That's exactly what we're measuring and trying to figure out and put right where we want it. So he just measured that. I think I saw it 144 hertz. Our target is a little lower than that. So what we want to do is give this top a little bit more flex than it currently has. Those braces stiffened it up a little bit more than we'd like.
These are real stiff, right?
Oh, yeah.
Okay, so they keep that top from moving, which is going to create the vibration. Okay.
But so what he's going to try to do right now is actually give it more flex, which means taking some material out of the bottom scallop of that X brace, right there where he's drawing his finger along. He's going to use a chisel and
pull some out of there.
Take some material.
Yeah. Nice and easy.
And you just do it right there by hand. Just grab a chisel and just...
Yep. It's the only way to really do it.
Wow.
It's the most accurate way you possibly can.
This is wild.
Yeah. We'll take out a little bit.
He's flipping it around so you can kind of meet those two cuts right in the middle so that nothing starts to break down the wrong direction or anything.
Yeah, you always want to go downhill from the grain with a chisel, otherwise you can get big bits of...
They'll generally do it to both sides.
You can like just dig into the wood.
Yeah.
And then he's ruined the top. Start
It's a
from scratch again.
little painstaking, and it's definitely a little bit of pressure goes into it because it's a very sharp object you're putting on the inside of this guitar. But
A little nerve-wracking, but you get used to it.
yeah, you do.
There we go.
Okay, so you've removed a little bit of that material. You've made that brace less structurally stable and
Now he's going to
strong.
measure it again and see exactly what that did there.
Let's hit it again. Okay.
See,
Oh yeah, he's moving down to right about on target.
right there,
140
So that
hertz.
little bit of material you removed.
So that little bit of material just removed 4 hertz from the overall fundamental frequency there. This might sound like gibberish to a lot of people, but it's actually, this is a process that has been happening, especially in the violin, cello, double bass era, for centuries now, for hundreds and hundreds of years. So it's what we call tap tuning the body. It doesn't mean that guitar is going to sound amazing when you play 140 hertz. Say, for ease of understanding this, say it's not 140 but it's 440, that will mean it's a perfect A. It doesn't necessarily mean that the guitar itself will be a perfect or sound brilliant in the key of A. It just means that what they're tuning there is the resonance between the top and the back plates. You want the top to have more flex than the back to be able to project the sound out. If the back is more flexible than the top, you end up with a box if you imagine the body as a box, which will just soak those vibrations and not project them out. So what you want to basically do when you're tap testing is measure that fundamental frequency of the top, make sure the back is stiffer, but then also tune it to like a fundamental root that both of those plates will work nicely together in, if that makes sense. So it's not like you're tuning the whole thing to one note and it's going to sound great when you're playing in that key. It means that the resonance and the vibrational energy of those plates are all working harmoniously. So it's doing its job in pushing the sound out, and that box working together harmoniously, because what you're doing is basically just sending vibrations through this box, and that generates the sound. So the more you can fine-tune the frequencies and the vibrational energies of each plate, the more sound you'll inherently have, and the richer harmonics you should have as well. So I hope that all makes sense. Let's keep going.
So you just tuned that top, so it's right where you want it.
Exactly, right.
Okay, and then you do that to the back as well. You're going to tune the back.
We do. We try to tune the back and top to kind of relate to one another, so we have targets for both. The targets change depending on body shape and stuff like that.
I see.
But yeah, so after he's done there, he'll just clean it up with some sandpaper so there's no rough edges on the inside. He'll do the same thing to the back and then send it back out to get built.
Well, I guess you have to tune the top and the back, because if you don't, if they're working in two different frequencies, those frequencies could cancel each other out.
Exactly. So we want to make sure that they operate in cooperation with one another, right? And make sure that, you know, when we tune this, we don't just send the back through on spec. We want them to interact with each other properly.
Gotcha.
So that's really what's important.
And every single guitar that we make here in Bend goes through this process.
Absolutely.
That's a lot of work.
Yes, sir.
And so these guitars are kind of awaiting their moment
Yeah,
to be,
these are more
to be analyzed.
that are getting ready to be chiseled a little bit.
Okay. So you put them together. You have the top, you have the back, you tune them, and then you're going to build the box, so to speak.
Yep.
We've shown that process if you watch a live tour video.
Right.
But we show the process of making the box. You put it together, and then are you done? That's it?
Oh, we got lots more to show you here. So
right,
I'll grab
let's
a body and I'll bring it in here and I'll show you guys what we do next.
Okay.
One thing I don't think I mentioned is that when they tune the individual plates, the thickness that they cut those plates to are going to be completely different every time, because the densities, the stiffness, the weight, all of that changes, and they've got certain frequencies that they want to be hitting. No two guitars will have the same thickness, well, maybe over hundreds, but they'll all have varying thicknesses between the back and the top and the sides, and everything will be tuned to a certain fundamental frequency.
So this is just phenomenal. I mean, that's amazing to see it just kind
It
of
is
tuned
very,
out in real
very
time,
interesting.
and to see the results expressed in a scientific way is pretty amazing.
So here's a finished body. It's all bound up,
Okay.
all glued up, ready to be inspected, and it's going to go through a little bit of sound optimization as well.
Okay.
Just to double check that we're on track with where we want to be.
Because you've added bracing, you've added the sides,
We've
you've changed
a lot.
you've introduced variables to this,
Right.
this
Oh,
whole
yeah.
process, right?
So we're going to check it out now that it's all together. Top and back.
So
You can
That's amazing. You can hear the difference in the tap between the top and the back. Let's just go back and show you that one more time. This is where I was saying that the back needs to be stiffer than the top. The stiffer and denser the material, the higher pitch that fundamental frequency will be. If you imagine, clanging a lump of wood, it will be just a dunk. But then do it on a bit of metal that's really dense and has very little variances. It's a ting, and it will ring through that whole bit of metal. So the more dense the material, the higher pitch the fundamental frequency is. And you can really hear that when they tap the top and the back.
added
there.
bracing, you've added
Listen
the
to that one
sides,
more
you've
time.
changed
a lot.
you've introduced variables to this
Right.
this
Oh,
whole
yeah.
process, right?
So we're going to check it out now that it's all together. Top. And back.
So you can see here.
And you can see on the chart that there's a good 30-40 degree hertz difference between the top and the back there.
The difference in the two on the taps.
Absolutely. Yeah, we want to tap both sides so we get a measurement of the top and back, which is what you're looking at with these two.
So those two are the bottom one's the top and the top one is the back. So the back's riding at like about 230 hertz and the top is riding at about 195 hertz.
Peaks here. You'll also see a third thing showed up now that we have closed the box and it's a finished body. We call this one the fundamental resonance. So that's the resonance of the entire body, not just the top or the back. That's kind of also showing, again, how these two are interacting with each other.
Gotcha.
And another thing we'll check here is to make sure that the separation, which is really important when it comes to our sound optimization process, is on target. So I'm looking at 194. Into 24, that's a difference of 30, and he's got a concert in his hands. This is the second time in a row where we've tested it, and it was literally perfect, so we're doing something right. There are changes we could make to this instrument in terms of the bracing on the inside, even with the box closed.
If you needed to.
If we needed to, but luckily we've nailed the process enough in the beginning that we're not going to need to get in there with the chisel or sandpaper or anything.
It's awesome to see that, you know,
obviously avoids any.
They're not just tapping blank sets of wood and then, you know, going, okay, that's good, glue it all together, stick it on the shelf, good to go. They're actually testing it every time they add mass, add material. It goes back into this room, it gets retested, making sure they're hitting their targets. It's great to see.
Any problems, because those things can come up when you get in there with sharp tools.
Well, that's super cool. So you've gone through the process, you've analyzed all of the wood from the very beginning, you've studied it to understand the inherent qualities and how you need to treat it in the build, even the play style that it could be. And then you have built a top with bracing, and you've analyzed this, you've carved away the bracing if necessary, you've built the box, put it together, done further analysis to understand that it's right where it needs to be.
Yes.
And then you're done.
Now we got one more thing.
One more step.
We got to keep checking on it and making sure that we're on target and that nothing strange happened, because, you know, this is just the body. There's a lot more parts that go onto this thing that can change.
Oh, you're going to put a bridge on, you're going to put on a finish.
Even the neck getting attached is going to change the numbers a little bit. Like, these numbers that you just saw are not going to be what the final numbers are. It changes. We just want to make sure we stay on target throughout the whole build process.
So let's check it out. Let's
That's
see.
where
Let's
we're
see
going to go next. We're back in the final inspection area. You guys might have seen in the tour video.
Yep. So this is the sound optimization final check station, right?
Yes, sir.
This is a magical little room. This is where all the guitarists get to sing their first song, play their first note, be heard for the first time.
Yeah.
Really cool room.
So they'll be checked
beautiful
for all the
guitars
normal
there.
stuff, obviously, throughout the build process. But we also check for sound optimization as well to make sure, again, nothing too crazy happened when they put on the neck and all the bridge and all the hardware and all that stuff.
So I see a Jeff Bridges signature organ model right there. What if we were to test that one?
You
If
can
we
grab
were
that.
Sure, let's do it. So same thing as we did with the unfinished body. We'll tap it on both sides.
So this guitar will be tapped. And now
So you can see there are, obviously it's a different guitar, but they're trying to hit similar fundamentals throughout the range. So the frequencies will be the same or similar, which would equate for the wood thicknesses to be completely different on the different types of guitars, but the different densities of material. So what they're trying to hit, they found like a sweet spot in these frequencies, and the fundamental and the resonant frequencies, and they're trying to hit that across the board on all of their guitars. It doesn't mean that all of their guitars are going to sound exactly the same, but it means that the vibe and like the characteristics will be similar. So you don't get, you know, we've all heard the story of, you know, Martin guitars. You get, because they're so highly mass produced, you get one which is golden, like the Stunner, the one that everyone wants, and then you get another one which is a bit meh, you know, and people that are after the right instrument may be hunting for it for years. The thing with Breedlove and doing this kind of procedure is they narrow that gap down. If you like Breedlove, if you enjoy their instruments, you'll really enjoy any of their instruments. If you're not a big fan of it, well, that's fine too. You know, it's just the way it is. So it is a little bit like they will cater really well for the people that really like their product, and they'll have a very consistent product across the board. So if you like a Breedlove, you'll probably like all of the Breedloves. So that kind of margin for, you know, having a great one and then having a not so great one is completely reduced via this process. So they actually are scientifically checking throughout every build stage what that instrument is doing in fundamental frequencies, weight, stiffness, and actually tailoring that to a certain kind of programmable end goal within frequencies. And this is something that really interests me. You know, before I got into guitar retail and guitars, I was running a small home studio. I did a course in sound design and studio recording, so I know a lot about, you know, fundamental frequencies, resonant frequencies, room frequencies, and all of that I learned in my degree in college, they have applied into woodworking. And it's something that I never really thought about until I saw this. I knew that tap testing was a thing, but I didn't think they got very involved. Just kind of thought it's like tap it. That is, you know, an A ringing at 440, let's go with that. But then once they close the box, it's like that's going to be completely different. However, Breedlove are basically saying that yes, we have tools, we can work inside the box once it's glued together. Once it's got a finish and a neck on it, we can still work on it, we can still fine tune it. If it doesn't meet our specs, then it doesn't go out, you know, it doesn't leave the factory. So it is a really different way of doing things, and I love the science behind it. I think it's really clever. You know, some people might think it's just a fad. However, the amount of work that they put into this, I think it shows some real passion behind what they're doing. But not only passion behind what they're doing, but a passion for understanding why they are doing what they're doing. Anyone can just, you know, go out and learn how to build a guitar. There's plenty of resources out there to do it, but are you actually fully understanding the materials you're working with? I don't think many people, you know, they can get into a woodwork shop and cut a bit of mahogany to a certain specification of size, but why are you doing that? And going into this process to understand what each material is doing and the differences between each material on a scientific level is something that I just love to see. It's remarkable, actually.
You have similar readings again. So he's got the reading of the top, the reading of the back, and this fundamental down here. That's the resonance of the entire instrument. And you can see it's a similar pattern, but these numbers did move around a little bit, I'll guarantee it, from where we measured it when it was still in whitewood.
And so if you're watching all this, I think, you know, an inherent question you're going to have is, why do all this work? What's the point? You know, this is a lot of work to do with these guitars. And my assumption would be that it's consistency in the sound,
exactly. Right? Right. We're trying to take out variability of the wood to make the end product as consistent as possible.
Yeah. Because I'm a guitar player, you guys are guitar players. I think we understand the experience when you're trying to find a guitar. You go to a guitar store. Absolutely. You play 1, 2, 3, however many of the same model, and you realize that they can all be a little different, right?
It's just, sometimes it just seems random. So it probably had something to do with the wood set itself, and I don't know if it it got analyzed as much as we're doing it here to try to figure out what made the most sense for that piece of wood. It probably was just built into a guitar from the get-go without any thoughts as to like what made the most sense for it.
Well, we talked about variability a little bit and
Yeah.
the fact that trees can vary up to 30% with the qualities of the tone wood. So if you just build a guitar and you have a spec and you say we cut all the pieces of wood to one spec and you treat it as such, you're going to throw these guitars together and you're going to have 30% variance in your final sound of your guitar, right?
A lot of them are going to sound different. And you'll get lucky sometimes, you'll get unlucky sometimes.
So 30% variance, but actually that could be more because a lot of companies, they use multiple different types of wood when building guitars. So the top would be one type of wood, the brace would be a different type of wood, the back and side plate would be a different type of wood, and the neck would be a different type of wood. Not that the neck has much to do with the overall tone, but the overall vibrational energy that gets sent through that instrument, it will make a difference.
And to eliminate both of those things and shoot for, get as close to it as possible.
So every guitar that you make, therefore, based on the type of tone wood, based on the body shape, you have target numbers that you want to hit. These are numbers that you've researched and identified. You hit those numbers every time.
And the last thing we'll do is record a lot of this stuff for the consumer. So
this is
it's
awesome.
got standard stuff on it. We call it a guitar portrait. It's got pretty standard stuff like a model and a play style and a serial number. But you can see we also weigh the instrument. At one point we will use a magnet ball to check the thickness of the top set of wood and the thickness of the back.
Nice.
I'll also write down these final frequencies that we got from our microphone over here. So you'll see we got a place here for the top frequency, the back frequency, and that fundamental.
Fundamental frequency, right?
Frequency of the entire instrument. And all this information goes on every card, goes with every guitar that gets shipped out.
This is amazing. And this sound optimization process, you know, I know that all these different tone woods, they all have really unique qualities. Some of them are so dense that they sink in water.
Sure.
Some are really light.
Right.
So this allows you to really understand how to get the most out of those tone woods as well, right?
And yeah, and on the upside too, you know, we're not just doing this stuff and then moving on. We're recording all of this
All the
for
data.
our own sake,
Sure.
so that we can constantly use this to improve the process, make things sound better, make little changes here and there to make the whole thing go smoother and sound smoother at the end of the day.
Well, and I know that it's also an R&D part of the process
Right.
for Breedlove. I mean, we have revolutionary body shapes. So this is a concerto. It's based off the concert shape, but it's larger and it would replace a standard dreadnought. It's big and boomy. But sound optimization was used to actually do the research and development to build this model, right?
Exactly, right.
And
So
so-
we use it in more ways than you can probably imagine. There's all sorts of things we can use this data for. So.
And I remember a story when you guys were engineering this body shape, you were building these and you were using the same sound hole that we'd use on our concert.
Right.
Your resonant frequency wasn't hitting.
It
So
was
you-
off a little bit, so we decided, well, one thing that we can change is how much airflow is able to get out, so change the sound hole size, which is exactly what we did here.
So you
with
shrunk
Wondershare.
the sound
Right.
hole. So this whole sound optimization process gives you data for engineering as well as
Right. It's not
consistency.
just about, you know, the top thickness. It can help us learn lots of different stuff about all the instruments that we build. So.
Well, this is super cool. I want to thank you guys for taking some.
That's a really interesting tidbit, that actually when they go about designing new instruments, they can use everything that they've learnt from previous builds to then have a good idea of what they want to achieve in the end product of a new type of body design, a new shape, a new type of tone wood that they've not used before, and actually really hone that in the research and development stage before they even release it as a model. So they're not going, oh, okay, everyone's using Koa, for instance, let's just buy some Koa and make some guitars from Koa. No, it doesn't work like that with Breedlove. They would buy Koa, they would build the bodies, they would research those frequencies and go, what can we do different to hit our, you know, tailored fundamentals that we want to hit, and you know, going all the way to let's change the sound hole size, you know, let's make the waist a bit narrower, a bit wider. All of those will have overarching effects on the end frequencies.
Time to walk us through this
Thank you.
process.
It's
wonderful.
This morning. Folks, if you want to catch some more videos here, you can check out the tour that Eric gave us of the custom shop where we build the guitar from start to finish. That's a pretty cool one as well. And yeah, thanks guys.
Yeah, thank you.
Okay.
Cool. So
Welcome
that's the
to-
end of the video. So I think within this video you can really see how technical a company can get and how few companies actually get this technical about things. How we go about things like setups here with our guitar repairs. We measure every little aspect of that instrument and give you a full sheet of pre and post measures, so you know exactly what the instrument was like when you brought it in and what we've done to it. But it also means that, you know, now you've got numbers, you can go, actually I want it a bit lower, a bit higher, I want to change this, I want to, you know, without that understanding of measurements, you don't really know what you want from the end product. The end product might be brilliant, but then you can't recreate that, you know, 100 times over. You know, you might recreate it a couple of times in 100, but what is really happening with that brilliant product? So measuring every step of the process, I think, will just narrow that gap right down. And like I said before, if you love Breedlove, you'll love every single one of them. You know, they're a very, very consistent product in tonality and playability. So yeah. Anyhow, this has been a long enough video, very technical video. Any questions at all, leave them in the comments. I'm happy to answer any of them. And yeah, cheers. See you in the next one, guys.